moving from our global temperature, global energy budget into this realm of the connection between increasing greenhouse gases and global temperature and then extremes. And so today I want to talk about heat waves and cold spells. But first, I want to talk a little bit about the difference between global temperature, which is what we've mostly discussed in this class, and local temperature. One thing to think about is to go back to, what are the causes of temperature change at the global level versus the local level. And so we talked about last semester this convenient finding in climate science that you can only change the global average temperature through these three mechanisms. That you can change how much energy is coming in from the sun, which has changed over time. The sun is variable in terms of how much radiation it's giving off to the Earth. Then you can change, how much of that solar energy is reflected back to space, or you can change essentially how much greenhouse gases are in the atmosphere, and then that changes the efficiency by which the Earth emits radiation to space. And so when you have more greenhouse gases, then it's going to be warmer. So thinking about this in terms of the local level, if let's just say San Jose, where I am anyway, experiences a cold week. Which of these three things do you think changed to cause San Jose to experience a cold week? Is it this one? Is it A, the greenhouse gas levels probably went down to make it a cold week? Is it B, that there was less incoming solar radiation, so the sun got darker? Is it C, that the albedo increased and that's what caused it to get cold for a week? And I'm not talking about seasonally. I'm not talking about that it gets cold in the winter and warm in the summer. I'm talking about that it gets cold one week and then warm the next week, so it just happens to be cold for whatever reason. Or is it D, none of these? And so it is actually probably D. So why do you think I'm saying that? Like, one thing is you have to be careful with the wording here, is that I have the word global in these things. So global reflected shortwave radiation probably decrease. So when we have like a cold week in San Jose, it's not because if you averaged over the whole globe, we saw that clouds, increased or something like that. So it's not C. It's not because the sun that week happened to get darker. So it's not B. And it's not because greenhouse gases fluctuate like that globally, right? And again, I have the word global here. Global greenhouse gas levels probably went down. So remember when we looked at like the carbon cycle and CO2 in the atmosphere, that is, that doesn't vary on week to week time scales, where all of a sudden 1 week there's way less greenhouse gases and 1 week there's way more, at least globally. So it has to be something else. I'm just trying to emphasize that this diagram here was for the global average temperature. So the global average temperature can only change for these three reasons. But the local temperature at any given location is going to be dictated much more by this additional factor, which in meteorology we call temperature advection. But really, all that means is that it's the movement of cold and warm air around the surface of the planet. So when you look at weather maps, you see cold fronts and warm fronts, and those just represent the movement of cold air and warm air. And so that's what dictates our temperatures locally, much more than these factors on kind of short time scales. And so that has big implications for how variable temperatures are at any given location compared to the global average. So let's think about that graphically. So if this is a cartoon version of the Earth here. So we have some continents and we have the ocean. And let's say this is our location that we're interested in. So no one lives in the global average. Everyone just lives at one location. So let's say you live here. And so what I'm going to want you to do is picture a graph of temperature. I'm going to show you some movement of air around the surface of the planet. I want you to picture what the graphs of temperature would look like at the dot. So what's the local temperature at the dot? So we have time on the x-axis, like a normal, time series graph. What's temperature going to look like at the local dot, at the red dot? And what's the global average temperature going to look like? So here's our situation. So let's say that for the sake of argument, the whole globe is 50 degrees Fahrenheit, except for two blobs. We have a cold blob of air up here, which is 30 degrees Fahrenheit. And we have a warm blob of air down here, which is 70 degrees Fahrenheit. And this is kind of the natural state of things, right? The climate system is we have warm air near the equator and cold air near the poles, just because of the way that the sunlight hits the surface of the planet. But the planet is spinning, and so it's constantly stirring itself up. The atmosphere is constantly being stirred up, and so we have warm and cold air masses moving around. And so what tends to happen is the cold air moves to the south and the warm air moves to the north. So watch carefully here for your graph. We have warm air moving to the north and then cold air moving to the south. So what is that going to look like on our graphs of local temperature and global average temperature? So here are your options. Which is the local temperature at the dot? Is it A, go 50 to 70 to 50 to 30? Is it B, 50 to 70, gradually down to 30? Is it C, 50 degrees the whole time? Or is it D, constantly decreasing from 70 to 30? And before I go over it, let's do the same question, but now the global temperature. So same options, but what's the global temperature doing? So the global average. So if I just average over all of those temperatures. So it's C. We have 50, and then, yeah, for the sake of argument, let's say these are the same area roughly, even though the warm looks a little bit bigger. So maybe it's really like 52 or something. But 50 plus, or 30, the average of 30 and 70 is 50, and then the rest is 50. And then when you're calculating the global average temperature, it doesn't matter where these blobs are, right? You can move them around all you want, and you still have 50 degrees the whole time. So that is just flat. So all of the movement, the point here is that all of the movement of air around the surface of the planet that can cause huge changes in temperature locally, that doesn't change the global average temperature at all. And then people, for the local temperature, it's A. That was kind of, a lot of people chose B. And I think that's, you're using your intuition. The temperatures don't change, like in step functions. But really the way that I made the animation, it is a step function, right? Because this is all 70 degrees, it's 50. And then when it's in the 70 degrees, it's abruptly in 70, then it's abruptly out of 70. And when it's in the 30, it's abruptly in 30. There's not any gradient here. So it's the answer to the local temperature is A. But I think if you chose B, you kind of have the right idea as well. Like in reality, it would look more like that. But what are the implications for temperature variability locally compared to the global average? Well, it's that variability is much greater, local variability is much greater than global variability. So it's A here. And so I just want to remind you, we've already, seen this in various forums, seen this phenomena. Like this is a video that we've looked at before of comparing the global mean temperature, same thing as the global average temperature, and looking at that spatial distribution. And so especially like when you look kind of in the modern global warming era, when we really start increasing temperatures, you can see that global average, there's some variability from year to year, but for the most part, it's just kind of monotonically increasing. But if you look at any given location, you can have, extreme hot, and then it gets colder, then it gets hot, and it gets colder again. And that just has to do with air moving around the surface of the planet, which is not going to be influencing this variability very much. So here's just an animation of temperatures from a weather model, and this is very similar to like what's going on right now in Texas, is that sometimes you get spillage of very cold air into the middle of the United States, and then it gets very cold, and then all of a sudden some warm air comes over. But like you can tell, like just by looking at this entire graphic, any given location can experience warm and cold, but there's no obvious change in the temperature of the entire area here. But that's one of the reasons why we have this very interesting situation where the global average temperature only varies from year to year by about 0.2 to 0.4 degrees Fahrenheit, despite the fact that we locally experience huge changes in temperature all the time. And it's because that dominant cause of the change in temperature is just movement of warm and cold air, warm fronts and cold fronts. So I want to tie this back to a phrase I used last semester called the signal to noise ratio. And if you recall, the signal to noise ratio, that can be defined a lot of different ways, but the way I was defining it is that the signal is the influence on some phenomena, the influence on X from human-caused greenhouse gas emissions. And then the noise would be the influence on that thing from everything else. And so examples of very high signal to noise ratio things were the concentrations of greenhouse gases in the atmosphere, that the influence of human emissions of carbon dioxide and methane and nitrous oxide just dominate the influence from everything else. So that's why we have these really dramatic kind of hockey sticks in the concentrations of greenhouse gases. And then another example of a high signal to noise ratio phenomenon is global average temperature. But we talked about that a lot of these extremes have low signal to noise ratios. So we're often in this zone where when we look back over the past 30, 50, 100 years, it's not obvious that there's even a trend in the thing that we're looking at, even though there might be some suspicion that as we put more greenhouse gases into the atmosphere, that thing will change in the future. And this lets you look at our temperature records in the United States going back to 1895 at the local level. So there's a lot of cities in here, but at least at the county level, you can look. And so what I want you to do is to pick the county you were born in, pick the month you were born in, check display trend, and pick the start year for the year you were born in. And I want you to see what that looks like. So here's the link. Here's what you would get when you go there. And so average temperature, I want you to keep as average temperature. Time scale, I want you to keep as 1 month. And then month, you would pick your birth month. Start year, keep the same. End year, keep the same. California, if it's California, you can go to any state. And then county is, let's stick with county instead of city. So whatever county. And then you do display trend. So you have to click this box here, display trend. And yeah, so if you weren't born in the United States, pick whatever you want. But this is limited to the United States, this website. So let's just do this. And then, yeah, so let's do display trend. And let's say you were born in 2000. The point of this is just to show you that weather is pretty chaotic at once you start drilling down to this kind of level of granularity, where you're looking at one location and you're looking at 1 month of the year and you're looking at a relatively short time period, like around 20 years. You can get negative trends in temperature over those periods of time. And that doesn't contradict anything we've been saying about global warming or global climate change. This is all of this data is embedded in those global graphs of temperature we've been showing you before. It's just that the atmosphere is constantly moving warm and cold air around the surface of the planet. And you can just kind of by chance get a situation where, you know, even over 20 years, you see cooling in a given month. But for the most part, you see warming. So most people got warming trends. So that's exactly what we would expect, to see more warming than cooling. You know, it's interesting to see when you have this lower signal to noise ratio, what that means in terms of like records being set. That in 2020, we did set a record for the warmest October in Santa Clara County. But in 2019, it was colder than it was in October 1932. You never get that in the global average, right? It's impossible that 2021 is going to be colder than 1932 in the global average. But it's very possible that any given location can be colder than it was at that location in 1932 next year.